Now we come to the important topic of harmonics. Harmonics relate to oscillations or waves, cycles, and frequency. Now, oscillations and frequency are inherent in everything. They're prevalent throughout creation. And this is enshrined in one of the fundamental principles of physics called the wave-particle duality. In other words, everything in physics everything in creation has both can have both particle and a wave nature. Now, if we take a simple system to look at how oscillations and waves arise in creation. So we'll take the very simple system of we say, a guitar string, for example, or it could be a piano string or whatever. So if we take a guitar string, the guitar string is necessarily fixed at two ends. So it cannot oscillate, cannot move two ends where it's fixed, but it can oscillate in the middle. So we get the most fundamental oscillation that can arise for that guitar string then is for it to oscillate about its midpoint, as illustrated here. So this gives a certain frequency. There's a certain frequency associated with that particular oscillation. So that is the foundational or the fundamental frequency associated with, say, a guitar string, or indeed with any physical system. Now, there's another possibility where we can get an oscillation, or we can get oscillations. We can also get two oscillations between the two fixed points. In other words, each half of the string can oscillate. So in this case, we have the two ends are necessarily fixed, and the midpoint is fixed, and the two halves then oscillate. So this creates a frequency that's exactly double the fundamental frequency of the first case. Now, this process can repeat. We can get three oscillations within the space of the length of the guitar string. We can get three oscillations as shown here. We get the string is divided in thirds. The nodes at the third wave points on the string are fixed, and then the thirds in between oscillate. And this process continues on up. We can have 4 oscillations within the string, 5 oscillations, 6 oscillations, 7 oscillation. Now, the fundamental frequency is associated with the basic oscillation, where there's just one oscillation across the full length of the string. The higher frequency oscillations are referred to as harmonics. So we have the fundamental frequency of the system, and then we have the harmonic frequencies associated with that fundamental. Now, the harmonics are whole number multiples of the fundamental frequency. So, for example, the second harmonic is double the frequency of the fundamental, the third harmonic is triple the frequency, the fourth harmonic is 4 times the frequency, the fifth, sixth, and seventh, and so on up the scale. The important point is that the harmonics are whole number multiples of the fundamental frequency of a particular system. Now, when we pluck a guitar string, or when we excite any physical system, we will get not just the fundamental, but we will also get a certain degree of each of these harmonics. In other words, we get the fundamental frequency as the strongest frequency in a guitar string. We get the harmonics then arising also to varying degrees. They will be much less than the fundamental, but they will be present, and they will be present to varying degrees. So the combination of the fundamental plus the harmonics create the tone that particular string produces. And it's this combination of harmonics that creates the difference between musical instruments. For example, the difference between, we'd say, a guitar string, piano, violin, or whatever. Now, the same principles apply we say, for wind instruments, we say in organ pipes. For any system that oscillates displays this behavior. The fundamental point being that the harmonic frequencies are whole number multiples of the fundamental frequency. And the combination of the fundamental plus the harmonics create the tone or the coloring of sounds produced or the oscillations produced by a particular system. Now we can look a little bit at a slightly more complex system where we have two strings, for example, where we pluck two strings on the guitar, and we look at how the frequencies of the two strings combine. In this case, we have one string oscillating at its fundamental frequency, and we have another string oscillating at a different frequency, but it's fundamental for that second string. Now, within a particular cycle of time, we can have a complete cycle of one frequency. If the second string has double the frequency of the first string, that means that we will get two complete cycles within one cycle of the first string. So that means that the two frequencies will combine to create a cyclic pattern of repetition. In other words, that pattern can repeat continuously, and it creates a harmonic combination of the two frequencies. In other words, where the second frequency is, or sorry, the second string has double the frequency of the first one, it is possible to combine, for the cycles to combine in a harmonious way. Likewise, if we have three frequencies, we'll get three cycles of one string, three cycles from one string combining with one cycle of the first string, creating a repetitive pattern, a pattern that repeats. And this creates a cyclic repetition, which creates harmony. In other words, we get harmonic repetition, a harmonic combination of those two frequencies. So where we'll say the two strings have frequencies in whole number relationship, these cyclic patterns arise and create harmony. So again, the fundamental principle of harmony is that the frequencies are in whole number relationship. Now we can extend that further. We'll say if the second string has a frequency of 1.5 times, 3 over 2 times frequency of the first string. Now in this case, for 2 cycles of the first string and 3 cycles of the second string, we get a repeating pattern. In other words, 2 cycles of the first string and 3 cycles of the second string will combine in a cyclic pattern, and that pattern will repeat. So that combination also creates harmony. Slightly more sophisticated harmony than we've discussed in the previous diagram, but it is still harmonic. It creates a more sophisticated harmonic relationship. So we can continue that process where the relationship between the frequencies of two strings can be expressed in as a ratio of whole numbers. Then the two frequencies will combine to create a repeating pattern. So for example, if the two frequencies are in the ratio of 5 to 4, that means that for 4 cycles of the slower frequency and 5 cycles of the higher frequency, they will combine to create a repeating pattern. So the fundamental principle for the harmonic combination of frequencies, of two frequencies for example, is that the ratio between the frequencies can be expressed as a ratio of whole numbers. Now the ratio of whole numbers is referred to as a rational number. In other words, it's a fraction. In other words, 5 over 4 is a ratio between two whole numbers, 5 and 4. It's referred to as a rational number. Now the simpler the rational number, the simpler this relationship, the lower the value of the numbers, the stronger the harmony. Now we can summarize all of that. Oscillations arise in any system. They can be musical instruments, they can be vibrations in an engine, or vibrations bridge or a building, or anything, and they will have a natural fundamental frequency. Now we will get additional sub-oscillations arise at whole number or integer multiples of this frequency, and these are known as harmonics, and they decrease in strength with increasing number. Now when we combine frequencies from two sources, for example successive notes in a guitar, piano or whatever, if integer multiples of the waves align, then the combination will form a regular repeating pattern. This arises, for example, when the frequencies form a ratio of integers of whole numbers, for example 3 to 2. The 3 to 2 frequency ratio means that 3 waves of the higher frequency will align with 2 of the smaller frequency, producing a pattern that repeats at a common fractional frequency. In other words, it will create a harmonic combination that will oscillate at a common fractional frequency. In other words, they harmonize. The smaller the ratio, the stronger the harmony. So the harmonic principle is that frequencies form whole number ratios, and the simpler the better, the stronger the harmony. Now this implies to any number of frequencies. Numbers that form such integer or whole number ratios are known as rational numbers, and these harmonic ratios were very important. And this principle was explored extensively by the ancient Greeks, and particularly by a group of the ancient Greeks who are known as Pythagoreans. They looked into this, and now they may not have discovered these relationships. Knowledge of them may have existed in earlier times, but they certainly studied them in great depth, and they developed a lot of the musical theory around them. Frequencies and harmonic relationships between frequencies are determined by number, and the most powerful numbers in harmonic structure are 2 and 3. 2 is particularly important because this is the simplest relationship, the simplest possible relationship between two frequencies. It's where one is double the other. And this doubling creates what are called octaves in musical terms, and these are fundamental building blocks of musical structure. The other important number is 3, and in the next slide we will see how 3 is used to divide these octave divisions into 12 subfrequencies. Another number that's quite important is 5. Now these 3 numbers, 2, 3 and 5, these are the most important numbers for looking at interdimensional structure and higher frequency influences. Now the Greeks took these two numbers, numbers 2 and 3, and they developed a number triangle as illustrated here. They took powers of 2 on one side, 1, 2, 4, 8, as in the crystal spiral expansion sequence, and powers of 3 on the other leg, and they formed ratios between these numbers. And these numbers defined harmonic ratios, which they used quite a lot. These are referred to as Pythagorean ratios. Now, these ratios were frequently used in proportions in building construction. So, as we saw with guitar strings, the length of the string impacted the frequency. So, frequency is associated with length and it's affected by geometry. So, the proportions of buildings, like the physical lengths and the proportions and the geometry of buildings, impacts on frequency. And so, there is harmonic relationship between lengths and proportions in buildings. And the harmonic principles are similar to those that apply to frequency. Now, we've seen that frequencies that form simple numerical relationships are harmonic. And conversely, frequencies that don't form simple numerical relationships cannot form a repeating pattern and are disharmonic. So, for example, if we have 2 frequencies, and if we can't take a fixed number of cycles at one frequency and a fixed number of cycles at the other frequency and combine them in the same period, if that isn't possible, then the numbers don't form a repeating pattern and they don't create harmony. So this is determined by numbers. Now, numbers like the square root of 2, 5, which is an expansion of the square root of 5, and square root of 3, these cannot be expressed as ratios between whole numbers. They're referred to as irrational, and as a consequence they are disharmonic. Now, the square root of whole numbers like 2, 3, square root of 5 and so on, these numbers become whole numbers for even powers. In other words, if we take square root of 2 and we apply it a second time square root of 2 by the square root of 2, we get 2, which is highly harmonic. So these numbers oscillate between harmony and disharmony. However, powers of phi, because they can always be reduced, as we've seen previously, all powers of phi can be reduced to numerical multiples of phi, and phi itself isn't harmonic, and multiples of phi are similarly not harmonic. So powers of phi never become whole numbers and are fundamentally disharmonic. Now, however, there are situations where disharmony can be beneficial, for example, in dividing clustering of leaves or branches on a tree. Now, we put this information to use in creating harmonic structures and harmonic scales. Now, frequencies expand naturally by a process of multiplication, similar to the spirals we've been discussing. So spirals provide a very powerful tool for looking at the structure inherent in frequencies. Now, the most fundamental harmonic relationship between frequencies is where the frequencies double. Notice where one is double the other. So we can create spirals where every cycle of the spiral corresponds to a doubling. This will correspond to a doubling in frequency. So this doubling in frequency is referred to as an octave. So we create these octave spirals where every cycle of the spiral corresponds to a doubling of frequency. So we've just illustrated 3 of the loops here, 3 of the cycles, the red, the green and the blue. But this process, if we were to follow it inwards on a reducing scale, it would converge, cycle progressively around the center and converge continuously to the center at 0. So we can organize our octave boundaries here along this vertical line. We can start, we'll say at 1, and then we have 2, and then we have 4, 8, 16, 32, 64, all the way up, 256, 512, 1004, and so on, where we're getting into more interesting frequencies. Frequencies are more interesting for sound and music. So we create our octave boundaries here along this clock line, this 12 o'clock line, and we draw our spirals in between, representing cycles. Now, these radii expand by 2 in stepping from each cycle outwards, or reduced by 2 and coming inwards. So these radii are these clock lines. They embody the power in doubling of frequencies. So they represent very strong elements of harmonic structure. In other words, all the frequencies along any of these clock lines are highly harmonic with each other. they're double each other and are highly harmonic. Now, the next stage in evolution of this structure then is to look at multiplication by 3. What happens when we multiply frequencies by 3? The doubling of frequency gives us the octaves, that provides us with the octave cycles. Now, multiplication by 3 does something very interesting. So when we multiply, we start with a frequency here, and we multiply it by 3. First of all, we'll pass through 2, directly above it, but then we will continue on past that point until we have trebled the frequency. The point at which we treble the frequency corresponds to the 7 o'clock clock line to a high degree of accuracy. It's not exact, but it is pretty close. So when we treble the frequency, we will move out to this 7 o'clock position, and then if we divide by 2, we'll come back in onto the same cycle. So this point here corresponds to a point 3/2 times the fundamental frequencies on the primary clock line. Now, the impact of multiplication by 3 is that we advance through 7 positions on the clock. Now, if we multiply by 3/2, we advance a further 7 clock lines. We go from 12 o'clock initially to 7, then we go from 7 hours on to 2 o'clock. Multiply by 3 again, we go a further 7 onto 9, multiply by 7, and we go further and come back to 4. So this process of multiplying by 3, if we repeat it continuously, it will take us through every single clock line. In other words, it will divide the octave cycle up into 12 units, 12 sub-frequencies corresponding to these 12 clock lines to a pretty good degree of accuracy. Now, this process of multiplying frequencies by 3/2, the 3/2 ratio is referred to as a fifth, and we'll see how that came about in a minute. So this process creates what's referred to as the circle of fifths. So the circle of fifths divides the octave cycles into 12 sub-frequencies that are evenly spaced around the octave cycle. So this creates a further level of structure within the harmonic scales. Now, after 12 cycles, we come around to we come back to the 12 o'clock line, but the error has accumulated. The original error in the alignment of the frequencies with the clock lines compounds through 12. It's multiplied 12 times, and it appears as a more significant error after 12 cycles. And this misalignment between 12 applications of multiplication by 3 and the 12 o'clock line position that we started with frequency, and it's referred to as a Pythagorean comma. Now, there are various ways for correcting for these slight misalignments. There are 2 approaches. One is to take the clock lines themselves, to take the 12 o'clock lines. In other words, take the octave cycles, which are very clear-cut, and divide them uniformly into 12 equally spaced clock lines where there is no error or there's no deviation from the clock lines. Now, that gives us what's referred to as the equal temper scale. In other words, the frequencies are uniformly spaced around the clock. And that makes it very easy to transpose frequencies, scales up and down. In other words, we can move up and down more easily through frequency scales because they're uniformly spaced. But it does sacrifice the purity, the harmonic purity. The harmonic purity is preserved by the simplicity of these numerical relationship between the frequencies. So 3/2 provides a very highly harmonic relationship between two frequencies. Likewise, 4/3 and on the 5 o'clock line is also highly related to these 3/2 on the 7 o'clock line, and that's highly harmonic. Now, if we pick freely from the clock lines and mix notes between them, there's a variety of relationships between specific clock lines. Now, the relationship between 2 frequencies is referred to as the interval between them, and in frequency terms, it's the one frequency divided by the other. In in angular terms, it's represented by the rotation, the degrees of rotation around these clock lines. In other words, the number of clock lines are the degrees of rotation or progression through the cycle of 12 sub-frequencies within each octave cycle. Now, some of these clock lines are more harmonic than others. The fundamental frequencies are represented on this 12 o'clock line as the octave boundaries. Some of these clock lines have more harmonic relationship with the fundamental frequencies and with each other than others. So, for example, if we take the 6 o'clock position, the 6 o'clock position is being exactly opposite the 12 o'clock position. The relationship between the frequencies on this 6 o'clock line and the 12 o'clock line are represented by the ratio between them is √2, which isn't harmonic. That is fundamentally disharmonic. So the most fundamentally disharmonic clock line in this collection of lines is the 6 o'clock line, is referred to as a tritone. Now, so 7 notes are selected. 7 of the most harmonic notes are selected from the 12 that are available, and these represent the strongest harmonic relationships. So we start with the octave boundary. Then we have the second note represented by relationship 9 to 8. We have a third note, fourth, fifth. So that's why the reference to the fifth in the circle of fifths is that the fifth note in this particular sequence of selected notes within the 12 available, the sixth here, the seventh, and then we'll come back to the octave at the eighth. And so that is how the term octave got its name. Now, the simple ratios preserve harmonic purity best. Now, when we go off these simple ratios to preserve equal spacing, we compromise the harmonic integrity somewhat, but it is a compromise. The alternative is to stick with the pure ratios in the important notes. And this is referred to as just intonation. So there are two compromises to compensate for the inexactitude of the alignment on these harmonic scales. Obviously, there is potential for more structure, possibly by bringing the powered number 5 into the picture. We can see that there are similarities between the crystal spiral and the octave spirals we have just been discussing, in that both expand by stages of 2. Now, where there is expansion by stages of 2, that means that every stage spans all the prior stages, and this also applies for octaves. So here we have laid out a sequence of octaves, with, say, increasing from 1 to 2 to 4 to 8 to 16 to 32. So if we take the current stage and overlay it on all of the prior stages, we will see that the current stage spans all of the prior stages. Now, each octave is divided into 12 notes, as we have seen previously. Each octave divides naturally into 12 sub-frequencies. Now, when we compare these frequencies with the boundaries of the earlier octaves, we see that there's a high degree of alignment between them. So, for example, the 7th sub-frequency corresponding to the 7th clock line we discussed previously, that aligns with the point halfway back. Now, there's a full octave back in the stages below. So it aligns very tightly with with a key octave boundary. Likewise, position 4 further back, or the sub-frequency 4 further back, aligns with another octave boundary further back again. 2 line up, the second sub-frequency lines up with an octave boundary, and the first sub-frequency lines up with an octave boundary further back. So there's a high degree of alignment then between notes within an octave and the boundaries of prior octaves, and this provides considerable harmonic strength. Now, dimensions are also directly related to or associated with frequencies and frequency bands. So the very same principles apply. This harmonic structure allows for a significant degree of alignment, harmonic alignment between dimensional bands. Now we'll just go back to a previous slide. Here we have a process that expands by stages of 2. This is the crystal spiral number sequence that we have encountered already, increasing in steps of 2. Now, as we saw with the crystal spiral number sequence, in expanding by 2, every stage encompasses all the previous stages. In other words, every stage reaches all the way back, connects all the way back to its point of origin at the center, at the 0 point, and it encompasses all of the prior stages. Now, this is important not only in ensuring connection back to the source, but it also facilitates alignment from lower levels, lower stages with the higher stages. Now, the very same principles apply to dimensions. We can consider these as dimensional levels, lower dimensional levels, and corresponding higher dimensional levels. Now, the dimensional bands are also subdivided into 12 sub-frequency bands. So every dimensional band has 12 sub-frequencies. Now, this structure facilitates alignment between the sub-frequency bands in higher dimensional levels with the frequency bands of lower dimensional levels. Now, this isn't possible with the Fibonacci number sequence, which is based on golden mean ratio. In this case, every number just connects to and encompasses the prior two only. So there isn't the same degree of connection all the way back to source. And because of this, it isn't as easy for lower levels in this structure to align with sub-levels in a higher structure. There isn't the same degree of alignment. So harmonic structure then is important, not only in not holding connection back to source, back to the point of our origination in source, but also in ensuring alignment through the different levels in the structure. So harmonic structure is very important in facilitating alignment up through the scales of dimensional structure. Now, in terms of alignment, frequency alignment, there are two frequency alignments of importance. One is the frequency to frequency alignment, where the frequencies are equal. We have a one-to-one alignment. The second is harmonic alignment, where the frequencies are not equal, but they have simple numerical relationships. They're connected by simple numerical relationships, which allow for harmonic behavior between the frequencies. So harmonic structure is of significance in working with dimensional levels. So far we've been discussing harmonics in relation to simple systems like guitar strings, organ pipes and so on. These are basically linear systems and basically 1D. And in this case we're fitting a fixed number of wavelengths into a particular length, we say the length of a guitar string. However, similar harmonic principles also apply to more complex systems where we have circular arrangements or where we have 2D or even 3D structures. So if we take the case of an atom with electrons orbiting around the central nucleus, now all particles have wave behavior. Wave behavior is fundamental to all in creation. Now, as an electron is spinning around the nucleus of an atom, it will oscillate on its pathway around the atom. Now, it will only take up orbits where a fixed number of these oscillations or waves can be accommodated around the path of the orbit. So this is similar to the principle of the guitar strings, only accommodating certain waves where you can fit a fixed number of oscillations within the length of the guitar string. Very same principle. So only certain orbits are possible that meet this requirement, where we get a fixed number of oscillations around, or wavelengths around the orbit or the circumference of the circle. Now in 3D, electrons form orbital structures within atoms based on these spherical harmonic principles. Here we have an illustration of some of the electron patterns, the electron cloud patterns, the 3D electron cloud patterns that form around the nucleus of an atom. These are illustrative of the particular structures that are possible and that arise in atomic structure within the electronic structure of the electrons orbiting around an atom. Now, these electronic structures are key to the physical and chemical properties of elements. They're also key to the molecular structure of groups of atoms, which are the building blocks of matter. These spherical harmonics are important in 3D structures generally. For example, the 3D structures of electric and magnetic and even gravitational fields, and even Merkaba fields. So the mathematics behind all of this is much more complex, but we're dealing with the same fundamental principles. So wave behavior is fundamental to creation and to what manifests in creation. Harmonics play a major role in creation. They determine the structures that arise within creation and how these structures interact. Spiral structures exist throughout nature and are a very powerful tool for understanding processes that arise in nature and for working with them. Now, the family of spirals that we've been working with here in terms of the crystal spiral, the golden mean and the Fibonacci spirals, these are a family of spirals known as exponential or logarithmic spirals, and that simply means that they expand by progressive multiplication or contract by division. Now, when spirals arise in nature, it's often assumed that they are Fibonacci, or that they can be related back to Fibonacci, or that can even be explained by Fibonacci. Now, these spirals exist as a family, as mathematical entities with very clearly defined structures, mathematical formulations, equations, and so on. They exist entirely independently of processes like the Fibonacci number sequence. In other words, their own separate identity and a very clearly defined mathematical identity independently of the Fibonacci number sequence, or indeed any such number sequence. Now, the structure of the spirals is very similar in terms of how they expand by progressive multiplication or reduce by division. Now, where they differ is in the rate of expansion. In other words, how fast or how slowly do they expand. So, for example, the crystal spiral expands by a factor of 2 for every 90 degrees of rotation, for every quadrant of rotation. The golden mean and the Fibonacci spirals expand by the golden mean ratio of 1.618. In other words, they're a slower spiral. Now, there are a huge number of other ratios. There are whole families of spirals with different expansion and contraction ratios. Now, in terms of expansion ratios for these spirals, there is a natural expansion ratio, a very powerful natural expansion ratio that is characteristic to this particular family of spirals. This expansion ratio is known as the exponential ratio. It's a number e equals 2.718. It's a continuous decimal. So that is the natural rate of expansion for these spirals, and that is the basis for working with these spirals in nature generally. It's not the golden mean ratio or even the crystal spiral ratio. It's this natural exponential ratio 2.718. Now, this is the base for natural logarithms, and it's also the natural exponent it is the exponent for expansion for natural processes. So this is the characteristic ratio for this class of spirals. It's not the Fibonacci spiral. It's not the Fibonacci sequence, or not even the golden mean ratio. Now, in examining these processes, there is a tendency to look for what we want. People look for the phi ratio, and they find that. Now, phi is a natural number, and it does arise in nature, and it is possible to find it. However, it's not the only one. There are many, many others. Now, the correspondences are often quite approximate, and there are lots of other ratios present that tend to get ignored because people don't know about them. Now, the harmonic ratios that we're looking at are very meaningful. In fact, they are more meaningful and more relevant in most cases. Some of these, such as we said ratio 8 to 5 or even 21 to 13, they are very close to phi. 8 to 5 is 1.6, which is very close to 1.618. So when we're taking ratios out in nature, the ratios tend to be variable, and we tend to pull them in close to particular values that we might be looking for. So where the phi ratio does arise in nature, or where it is found in nature, it can be fairly approximate. Harmonic ratios have physical impact, and they can often be more relevant to the situations where spirals are found. Now, our Milky Way galaxy has a general spiral structure, illustrated here. Now, the expansion ratio here is much slower than either the golden mean or the Fibonacci or the crystal spiral. Now, we can measure the expansion ratio for any of these spirals by just taking a diameter through the center across the arms of the spiral. Measure the radius from the center to one side and the center or the radius length to the other side, and divide them. Now, that gives us the rate of expansion for 180 degrees, or for 2 quadrants. So we just take the square root of that number to get the actual ratio for the quadrant ratio for rotation through 90 degrees. Now, take those measurements for the Milky Way galaxy. We get a figure that's closer to the square root of 2. In other words, it's much lower than either 1.618 or the value of 2 for the crystal spiral. Also, in human anatomy, a lot of the proportions are claimed to be golden mean. For example, the ratio of hand to forearm. However, there's huge variability to the point where such ratios aren't very meaningful. And even in the case where these ratios are quantified or illustrated in terms of the Vitruvian man. The ratios in the Vitruvian man are more representative of harmonic ratios. Now, people do try to fit golden mean in as the ratio or as a relation between the square and the circle in that particular diagram, but that's quite approximate, and in fact is more accurately described as a harmonic ratio. Also, the famous Nautilus shell, which is often used as a symbol for the Fibonacci spiral and for Fibonacci processes in general. Now, the Nautilus spiral is generally much slower than the phi ratio. Again, if we take a measure of the rate of expansion of this, it's somewhere for this particular illustration, it's somewhere in the range of 1.35 to 1.4. Again, much less than the phi ratio. Also, in ancient architecture, Greek and Egyptian, these use many ratios. Some of them are harmonic, some of them are GM, and some of them are other ratios again. So in Greek architecture, in the temples, for example, the proportioning of the Greek temples, there's a variety of ratios in use, and many of them are harmonic in nature. Now, in the case of the pyramids again use over a variety of ratios. They use the 3-4-5 triangular ratio, the Pythagorean triangle ratios. They also use harmonic ratios, and some of them do appear to use golden mean ratio. In looking at, we say, ancient structures like the pyramids, we must recognize that the stone has actually gone off these structures at this point. So the proportions that are measured at this point in time are estimates of what it would have looked like when it was in its intact state. Now we take a brief look at a different topic, the topic of Merkaba. Merkaba is a system for distributing dimensional energies. Now these dimensional energies arise in two polarized forms. One polarity is electrical and the other polarity is magnetic. Now there's a framework for supporting these energy flows, and it takes the form of two tetrahedra. Tetrahedron for electrical polarity and another for the magnetic polarity. Now these tetrahedral structures, they're basically three-sided pyramids. They have an apex at the top, and then they have a base with three corners. And so we have the electrical vortex flowing in from the apex at the top of this upper pyramid, this upper tetrahedron. It flows in, distributes through the tetrahedral structure as electrical energy. And we have a similar vortex of energy coming in from the bottom, a vortex of magnetically polarized energy coming in from the bottom through this the point of the tetrahedron, coming in through the tetrahedral structure and distributing within the tetrahedron. Now these two tetrahedral or pyramidal structures, they're interleaved as illustrated here. The upper vortex of electrical energy, the lower vortex of magnetic energy. The energy comes in as a swirling vortex of energy, and it is spinning. The two energies are spinning. Now, being polarized and of opposite polarity, the spin directions of both vortices are opposite. So we have a vortex of energy coming in through the upper electrical pyramid that spins clockwise down through the pyramidal structure, and we have the opposite vortex of magnetic energy coming in through the bottom and spinning upwards in a counterclockwise direction. So this sets up an energy distribution within the combined pyramidal structures, and it can be illustrated as follows. So we have the electrical energy coming in through the top of the apex of the pyramid of the tetrahedron, flows down through the center point of the structures. It then flows down here as the yellow flow of energy back through the center, and then it flows back out through the point through which it entered. We have a similar circulation of energy for the magnetic flow, coming in from the bottom, going through the center, looping around, back through the center, and then looping around on the other side, and then going back out through the bottom. The two vortices are spinning in opposite directions. They interact and they set up this flow or distribution of energy within the structures. Now we're just showing a two-dimensional section view through the arrangement here, but we can visualize that they are actually three-dimensional. So these would represent donut type structures. It is basically a three-dimensional flow of energy. So the Merkaba flows are supported by a framework, and this framework consists of the two tetrahedrons. Now, the conventional view or visualization of Merkaba is that these tetrahedra spin. Like they're often sometimes viewed as solid structures, and they are often viewed as if they're spinning. That the upper one is spinning clockwise, and the lower one spinning counterclockwise. Reality, however, it isn't necessary. It is the energy fields themselves, the electrical and magnetic energy fields themselves, that are doing the spinning. Now, it isn't necessary for the framework to spin. It isn't necessary for the tetrahedra to spin. The spinning effect in the circulation can be achieved by having the three base points phase in rotation. In other words, this switches on, drawing a circulation of energy down from the apex. This switches on, and then this switches on, or phases a short while later, pulling the energy in this direction. This then phases, pulling the energy in this direction, and then this phases, pulling the energy in this direction. So these base points don't need to move. They can just phase, and in doing so, they set up a circulating field. And this field then circulates the electrical energy within the structure, within the framework. Likewise, for the bottom, the points can phase, but in the opposite sequence. So they can phase, the three base points can phase this 1, 2, and 3. And in doing so, they set up a circulation of energy, for circulation for the magnetic vortex of energy that's coming into that pyramid. Now, this configuration isn't unusual. This is exactly what happens in large electric motors. In large electric motor, you have coils, field coils. The field coils themselves don't move, but the electricity coming into them phases in sequence. Like you have three coils around the frame of a motor, and the electricity peaks in each of the coils in sequence. The sequence in which it peaks in the coils determines the direction of rotation. So the phasing of the three coils sets up a circular rotating magnetic field, and this actually pulls a magnet on the axle of the motor, and that causes the motion. So the framework of the motor itself doesn't move, but it does create moving fields, and these fields cause motion, which can be transmitted out through a shaft. And so this phenomenon of phasing causing rotating fields, is actually quite widespread in nature. So it isn't necessary for the tetrahedral structures to actually move at all, and they don't even have to be solid. They just represent a sequence of phasing points. So Merkaba is associated with a symbol called the Merkaba star. The Merkaba star, it's the six-pointed star. It's often also referred to as the Star of David. Now, this is a representation of Merkaba. Now, if the tetrahedrons were rotating, these two triangles would be counter-rotating past each other. And so the Merkaba star wouldn't be a realistic representation of what was going on. So the Merkaba star indicates these set 6 points in a fixed alignment. And that is to support that the tetrahedrons are not moving. Also, in doing energy work, this Merkaba star configuration is a very powerful configuration for energy work. Notice when people are doing energy work, they can stand in these positions. They can take up these positions in the Merkaba star formation around a particular point that's being worked on, or whatever is being worked on. And they can phase in sequence. They can run energy in sequence, and in doing so, they can work very powerfully with energies. Now, there's a more powerful formation containing 12 centers that is used, for example, in the rainbow roundtables to run very powerful streams of interdimensional energy. You can set up pillars of sound and light. Now, this Merkaba structure sets up an additional structure within the energy fields of a person. So our personal Merkaba fields, they set up an energy distribution, but they also set up a layer of dimensional energy within the energy fields. Now, there's a Merkaba field and an associated Merkaba framework, and a set of Merkaba electrical and magnetic fields for each dimensional level from 1 through 12, all the way up. Finally, for interest, it's interesting to compare the Merkaba field patterns with some of the electron field patterns around an atom that were illustrated earlier. Now, for another point of interest, we look at scaling proportions and how they're affected by dimensionality. In 2D, when we embed elementary structures within each other, they tend to scale by a factor of 2. So, for example, if we take nested triangles, we take a triangle and we contain it within a circle, and then we embed that circle within the bigger version of that triangle. And the scaling between the smaller and the bigger triangles is 2. Likewise, if we take a Merkaba star, the star of the 6-pointed star, if we embed that completely within a bigger version of itself, the proportions between the two are 2 to 1. Now, if we take the example of a square, in the case of a square, you can have a square rotated 90 degrees that contains a smaller square. Now, the green square that's rotated is root 2 times, the proportions are root 2 times the smaller square. If we repeat that process to get the bigger blue square, then the blue square, which aligns with, in other words, is parallel to the smaller square, in this case, proportions are 2 to 1. Now, if we take the case of 3D, and we can repeat this exercise, the triangle is replaced by the tetrahedron, the pyramid that has 3 sides and a base. Now, contain that within a sphere, and then build a bigger pyramid around that. Now, the proportions between the smaller and the bigger pyramid are 3 to 1 in this case. And the same would apply if we embedded 2 tetrahedra in each other as for the Merk structure. The same proportions would apply. Now, if we take the case of a cube and we contain that within the bigger cube that is rotated, then the bigger cube is root 3. The proportions of the bigger cube are root 3 times the smaller one. Now, we do repeat that process again, so we get the bigger cube, the blue cube, that is parallel. The sides are parallel to the smaller cube. In this case, the bigger cube has proportions 3 times the smaller one. So it's interesting to observe this scaling. Now, the numbers vary a bit as we go up in bigger numbers of sides, elementary structures. Now, we live in a 3D world, but at the same time, a lot of our interaction with the world is actually 2D. So when we're dealing with maps, diagrams, information on paper and so on, that's all 2D. Also, when we're working with screens, again, that's 2D. So a lot of our interaction, or the information that we exchange with the world is at the level of 2D. Also, if we think of moving around on the surface of the Earth, we can move freely into 2 horizontal dimensions, but it's more difficult to move in the vertical dimension. In other words, as our weight and the force of gravity impede movement in the 3rd direction. Now we can summarize some of the geometries we've been discussing. We can summarize their elementary shapes and their associated numbers. The triangle obviously is associated with the number 3. The square is associated with number 4, with its 4 sides. It also embraces the numbers 2 and the square root of 2 as a diagonal key measure within the squares. The 5-sided pentagon is associated with number 5. The phi is intricately associated with pentagonal geometry. And for the 6-sided hexagon, it's associated with numbers 3 and 2. And its chord across the structure is square root of 3 in length. Now, going back to the pentagonal geometry, this is highly associated with number 5. Number 5 is characteristic of this geometry and is inherent in it. So when we take 3D solids, for example, that encompass the pentagonal geometry, for example, the dodecahedron and the icosahedron, these are 2 important Platonic solids. They are closely related in that they can be transformed one into the other. Now, these solids embrace both the pentagonal geometry and the triangular geometry. So the pentagonal geometry and its associated phi is actually baked into those particular solids. So when we take those solids and we extend them on phi ratios, it's interesting, but it's not surprising that we see a lot of pattern emerging when they are extended on phi, on scales associated with number phi. In other words, the phi is baked into the foundation of these structures, and so it will emerge in the structures associated that derive from those structures. In other words, what we put in, we're basically getting back out of those particular structures. Now, if we extend these figures with their numbers of sides, eventually come to the circle, which is an infinite number of sides. And this is associated with number pi equals 3.14. This is the characteristic number associated with circles. Frequency is inextricably associated with circles. Circles generate waves, generate cycles of repetition, which generate frequency, which in turn generate waves. So frequency is inextricably associated with circles and circular motion. Now the next construct we meet is the exponential growth curve. This is associated with growth and decay. It's an important element within creation, the patterns of exponential growth and decay. The number associated with exponential growth is this number that we've mentioned previously, e equals 2.718, and it's a continuing decimal. Now this is a very powerful number. Growth and decay and frequency are both encompassed within spirals. There are two key features of spirals. We have the spiral, the expansion of the spiral, the exponential expansion of the spiral, and the exponential decay of the spiral on the contracting phase. So the rate of expansion and contraction is determined by the base for the exponential growth curve. And the natural base for expansion is by factors of 2.718, this number e. This is an extremely powerful number. It's fundamental to all of mathematics and all natural processes. Because this process, this exponential curve and the mathematics behind it, it embraces both circular motion and growth and decay, and both of which are also encompassed within spirals. So this is foundational to an awful lot of processes in nature, and it's probably the most powerful number in mathematics. Now, it has some very interesting features. When we were looking at number 2, for example, we saw that exponential growth on the base of 2, in other words, a doubling through every cycle. This gives us a unique feature where every stage of expansion encompassed all of the previous stages. Now, this feature is also inherent in the exponential growth curve. So if we take any point on an exponential growth curve, that point is equal to the sum of all of the previous points going all the way back to 0. In other words, it's equal to the area of the curve, under the curve, all the way back to 0. Now, the difference between them is that the exponential growth on the base of 2 is associated with discrete processes that work with whole numbers, whereas this is an exponential process. It works smoothly and continuously across all numbers. In other words, it includes not only the whole numbers, but also all of the numbers in between. For example, all of the numbers between 1 and 2, all the decimal numbers, and so on. So this has a unique property similar to exponential growth on the base 2. It has the same unique property, but in a more powerful way, in that every value is equal to the sum of all the previous values. In other words, every value is equal to the area under the curve all the way back to 0. So that's a very powerful feature, and it's unique to this particular number. Now, furthermore, a feature of exponential growth is that the pace of growth, or the rate of growth, increases as the growth itself progresses. Now, this base for exponential growth also has the very powerful feature that the rate of growth at every point on the curve is equal to the state of growth. In other words, as the growth progresses, it gets faster and faster, progressively faster. So this is very powerful behavior. Now, exponential growth on the base 2 and exponential growth on this base 2.718 are very closely related. And the number 2, this number here can actually be derived from the number 2. The two are closely coupled, and the processes behind them are closely related. Now, in terms of importance, these are the two most important ones in terms of practical application. And when we're talking about pi, we're talking about the real pi, not like J and pi, for example, is an approximation to this, and wouldn't be accurate enough though for a lot of circular work. Now, if we look at 3D solids and their associated geometries, the most interesting examples of such geometries are, and their associated structures, are crystals. Now, if we take water as a medium for crystals, water is a very powerful medium. It can be easily imprinted with energy patterns, and it's very good for carrying information. and it's very open to influence. Now, these are examples of water crystals. In other words, when water freezes to form ice crystals or form snowflakes, we get these very intricate patterns which basically follow hexagonal pattern. In other words, their geometry is fundamentally hexagonal. Now, there was a lot of interesting work done by a Japanese scientist, Masaru Emoto. He imprinted water with various influences, both positive and negative. In other words, he imprinted thought patterns into water, positive thoughts of pleasant environments, and also negative thoughts. And he then froze the water to reveal the structures, the ice structures, or the ice structures that would emerge from the water that had been imprinted. And what was very interesting was that the energy influences and information that was imprinted into the water actually reflected in the crystals. It influenced the crystals and reflected in them. So I got discordant patterns or negative thoughts or negative influences, more beautiful and regular patterns or structures for positive influences. All of the ice structures formed were fundamentally hexagonal in nature. In other words, hexagon was the fundamental shape underlying crystal patterns that were formed. Now, there's a reason for this. It comes back to the classical formation of crystals. Now, crystals form when groups of atoms collect together to form molecules, and then when those molecules come together to form clusters, they form cells. Now, these cells, they generally build up in 2D sheets, and they fill the space in the sheets. The geometry of the cells grows in such a way that they fill the space available to them within the 2D sheets. So in the case of water, the water atoms and molecules come together to form these hexagonal cells, and these hexagonal cells cluster together to fill the 2D space of the sheet that they're forming. Now, these sheets build up on top of one another, build up vertically on top of each other to provide a 3D element, third dimensional direction. Now, there's a reason why hexagonal pattern arises. A typical cell structure for the formation of crystals. Here, for example, we have an example of a crystal, a solid crystal, and it has a basic hexagonal pattern, a basic hexagonal shape. The angles on the edges are 120 degrees. Now, there are certain patterns that favor the formation of these cells, and there are other patterns that don't. Now, the basic idea is to fill the space, the horizontal space, as efficiently as possible. Now, the hexagonal pattern is very efficient at filling the space. Hexagonal or triangular patterns, because the hexagons can always be split up into triangles. They are closely related. So hexagons are very efficient for filling space, and this is referred to as tiling space. In other words, it's like the process of tiling a wall. You fill the available space with the elements of it, with the tiles or the elements that you're working with, or in this case, in case of crystals, you fill them with the cells that the molecules are forming. Now, the other pattern that's regular pattern that favors the formation of these crystal cells is a square or a rectangular grid. In other words, four-sided figures. They are very efficient at filling space. In other words, they are a regular tiling pattern, just as hexagons are a regular tiling pattern. Now, when we come to pentagons don't fill space so efficiently. In other words, when we pull them together, there's a gap. The angles don't add up. They don't fill the available space. So there is a gap between the pentagons. Likewise, for octagonal figures, they overlap. In other words, if we cluster them together, they overlap. In other words, they clash. They don't fit together smoothly as for the 4 and the 6-sided figures. Now, for this reason, pentagonal patterns are not characteristic of normal crystal formation, and neither are octagonal patterns. Now, the pentagon can arise in crystal structure in forms that, like dodecahedron, the icosahedron, or the buckyball structure. Buckyball starts out as an icosahedron. If we cut off the corners, form a soccer ball type structure, we get a rounded structure that's based on pentagonal geometry. And also, it also includes hexagons. Now, creation is all about life, and so the purpose of forms is to embody life. In other words, to allow life to use the form, be present in creation, and to impact creation. So the efficiency by which these structures engage life and allow a flow of life through them and out into the environment is key to the efficiency of crystals. Now, the structures that we've been talking about, where you have sheets of crystal cells and they stack vertically on top of each other, this structure is open in the third dimension. And so this is amenable to the flow of influences, the flow of energy, higher dimensional energy, life force energy, and influences into these structures, to be held in those structures, and then to interact through those structures with creation. So the openness of structure is a key requirement for crystals to be effective in creation. So that is a key, that is a desired feature in crystals, is that there is enough openness in the structure to allow influences, higher dimensional influences, to move into and through them. Now, when we work with structures like the dodecahedron, the icosahedron, or the buckyball, these unfortunately are closed structures. The pattern closes around itself and it's effectively sealed shut. So they're not very efficient for allowing higher dimensional influences to enter into them and to work through them. So this is an issue for those crystalline patterns that are based on these structures. Now, with the pentagonal geometry, it is possible to form crystal arrangements using these sheets. A very famous English scientist, Roger Penrose, he developed a process for cutting these pentagons up into, in other words, cutting some of the pentagons up into smaller shapes and using those smaller shapes to fill in the gaps. So he developed a process for tiling these sheets using what's referred to now as Penrose tiling. So this allows pentagons to be used to form 2D sheets of crystalline structures. However, the patterns are not regular as they are for the square or the hexagonal patterns or hexagonal cells. In Penrose tiling, the pattern is continuously varying. So it's a more complex pattern, is continuously varying. And the crystal formations that are derived from this, they're referred to as quasi-crystals. In other words, they're not conventional crystals, they're a very, very specialized form of crystal. So these quasi-crystals, they do use pentagonal geometry, and we'll say things like the buckyball, the soccer ball formation, which is derived from the icosahedron, that also can form crystalline structures, but crystalline structures are closed in nature, which is an issue for them. Now, coming back to our geometric patterns, in principle, all of the patterns have their own value and are sacred in their own way. But one of them in particular has been singled out as sacred geometry in a lot of sacred geometry work, and that is the pentagonal geometry. So if we were to pick out one of these patterns, very powerful, as being worthy of being exalted, which one would we choose? In practical terms, these are the ones we would choose. These are the most powerful ones. But pentagonal geometry is often regarded as sacred, as being key to sacred geometry. And we can ask the question, why is this? Why is it exalted in sacred geometry work? Now, there is a reason for it, and this takes us into what we will discuss next, and that is the energy grids associated with our universe and historical events associated with those grids. Now, the issues involved have more to do with politics than with geometry. In other words, their core issues are political in nature more than geometric.